Hi, everyone. Welcome to one of these three university seminars. This is a joint space physics seminar between UNH, Virginia Tech, and Rice University. So I think we have folks from all of the three schools there. Today we are having Kevin Pham from NCAR High Altitude Observatory presenting to us. Kevin has received his PhD from University of Texas in Arlington in 2016. He worked on global magnetosphere responses to solar wind high-speed streams using global MHD simulations at the time. He worked with Ramon Lopez at UTA. After that, he did a postdoc at West Virginia University and then a postdoc at NCAR. And as of just this last Monday, Kevin is a project scientist at NCAR. So congratulations, Kevin. Kevin is going to talk to us about his coupled simulations of the magnetosphere, ionosphere, thermosphere system, and about how high resolution of these simulations helps him to answer various science questions. So Kevin, take it away.
Thank you for the introduction, Slava. All right, so I'll talk a little bit about capturing the spatial and temporal variability of geospace. Geospace is pretty large, so I'll focus more on the interface between different models and the different regions of geospace. All right, let's see. All right, so I'll discuss geospace in general and what are the different regions of geospace, and then discuss what are the models to describe the different regions. Discuss a little bit about numerical resolving power. What exactly is numerical resolving power? Why is it important? And how is it applied? Discuss a little bit about neutral density, and then data metrics at the very end. All right, so before we start discussing geospace, we first need to look at the sun. So the sun is this ball of plasma that rotates, continuously rotates. It takes about 27 days from the point of view of Earth to rotate once. And then as it's rotating, it's constantly shooting out all these vectors. So for what we do, these vectors are normally either magnetic field vectors and velocity vectors coming out. So it's the solar wind velocity and solar wind magnetic field, also known as the IMF, or interplanetary magnetic field. And then in addition to vectors, it also has a few scalars such as temperature and density. So those are just a few things that we care about as far as the solar wind that's coming out. Once it shoots out a bunch of vectors, in addition to vectors, it also shoots out a lot of particles. These highly energetic particles can reach the Earth, and then it'll produce, or not particles, but it'll also shoot out like EUV light that reaches the Earth and then starts ionizing the Earth's upper atmosphere. This produces a lot of ionization, this produces a lot of ions, and then the ions can then get accelerated through the upper atmosphere and then escape into the magnetosphere. In addition, the solar wind itself is it's quasi-neutral, so it has a lot of ions and then electrons. So when you look at things on a larger scale, it's relatively neutral, but when you boil it down, it's a lot of ions moving, it's a lot of electrons moving. So that gives us a charged plasma, and then that surrounds the Earth and pretty much everywhere else in space. And then I'm going to talk about how this interaction plays together. All right, so now I'll discuss the different regions of geospace. So I just mentioned geospace. What is geospace? It's a noun, it's uncountable. It really depends on how you separate the different regions of geospace. Some models will include multiple regions together. Some models will overlap with other models. It just, you can define it however you want it. The region of outer space near Earth, including the upper atmosphere, ionosphere, and magnetosphere. So it's just really anything around Earth. All right, so here's a quick diagram of what geospace looks like. So you have outer space up here, magnetosphere, which can be separated into many individual regions, such as the inner magnetosphere, the outer magnetosphere, the lobes, the plasma sheet. There's all sorts of structures up here, but in general, we'll just treat it as the magnetosphere. It's a lot easier that way. As far as the atmosphere, typically when we say atmosphere, we're discussing the neutral atmosphere. So it's all the neutrals, all the air around us right now is relatively neutral. So you have the troposphere, stratosphere, mesosphere, thermosphere, where it starts heating up and getting hot, and then the exosphere. So these are all the neutrals going up. So the upper atmosphere is typically the thermosphere and the exosphere. The exosphere is really difficult, so we'll kind of ignore the exosphere for now. We'll just go from the thermosphere and then jump directly to the magnetosphere. We'll just call the exosphere the gap region. It's this mysterious region that we don't know much about. And then the mesosphere sometimes is included as part of the upper atmosphere. It's more like the middle atmosphere. And then you have stratosphere and troposphere down below. This is where all your typical earthly weather is. So that's the neutral stuff. So if you go to the ions, then the charged stuff, you have ozone, which is at the lower atmosphere here. We don't care too much about what the ozone is doing in this coupled model, but then you have the ionosphere. So the ionosphere typically overlaps with the thermosphere, and then extends all the way up to the magnetosphere. So it overlaps with the exosphere region, but since it's kind of the same physics going up, the ionosphere, a lot of individual independent ionosphere models will go from the bottom of the thermosphere and then go all the way towards to the magnetosphere and potentially beyond. And so we'll focus a little bit more on the thermosphere, ionosphere, and the magnetosphere. And then this is the gap region, like I mentioned earlier. All right, so how do these different regions couple and interact with each other? It's through a very complex process. This is a picture from NASA. So as far as NASA is concerned, we don't know a lot about what's happening. You can see that individually there's magnetospheric driven ion convection here, auroral heating region. There's just so many things going on that is incredibly difficult to just look at one thing at a time. So what you have to do is put everything into a model. You have your solar wind magnetospheric chain here as a single model. Potentially solar radiation is either a model or a subset of your model. You have the lower atmosphere, which is potentially another model. And so everything is just, you have to put everything into a model because it's so difficult to try to figure out what's happening and try to trace one particular phenomenon and then what happens to everything else. All right, so now let's quickly discuss what are the different models, how the models are used, and the models of the different regions. So first off, as part of SLAVA's CGS, the Center for Geospace Storms, we use the MAGE model, the multi-scale atmosphere geospace environment. So this MAGE model incorporates TIGCM, or the thermosphere, ionosphere, electrodynamic journal circulation model, which is the model of the ionosphere upper atmosphere. There's also REMIX, which is the ionospheric electrodynamics model. There's Gomera, which is the global magnetosphere model. And then there's RCM, which is the ring current model. Well, RCM does not stand for ring current model. It stands for the Rice convection model, which is a ring current model, not to be confused with other models of the ring current. So the nice thing about what we have with the MAGE model right now is that it is the highest resolving power geospace coupled model to date. It couples all these regions to very high resolution, and it's not just the resolution, it's also to very high numerical solving scheme. And so it's not about the size of your grid, but it's how you use it. It's all about the resolving power. It's how you resolve the structures and how you propagate the structures and what you do with your grid that's important. So what I'll be talking about is Gomera will be running at what we call octres, which is approximately a 1/4 degree in the ionosphere. So REMIX, which is the inner boundary of Gomera, is running at about a 1/4 degree, or not a 1/4, a 1/2 degree in REMIX. That's mapped to TIGCM, which runs at 0.625 degrees. I honestly don't know why it's such a funny number, but you have 0.625 degrees in TIGCM. And then RCM runs at, for the latitude grid, it's about a 1/4 degree. And then for the longitude grid, it's about 1 degree. So coupled together, this is the highest resolving power geospace coupled model there is. All right, so individually, TIGCM is an open source model. It's an NCAR maintained model, developed and maintained by NCAR. It's a model of the ionosphere thermosphere. It starts at about 97 kilometers and it goes up to about 500 kilometers-ish. The reason why there's this ish is because the altitude isn't defined by height, it's defined by pressure level. And so as you heat the thermosphere and expand your upper atmosphere, then that, for given pressure, your pressure level moves to a higher altitude. And so it will, so depending on how the thermosphere expands and contracts, that changes your upper altitude. However, your lower boundary is still the same at 97 kilometers. This is widely used by the this model is widely used by the ionosphere thermosphere model because it's open source, it's well maintained, and it's easy to install and run. And then recently, as of the past 2-3 years, we've increased the resolution from a maximum of 2.5 degrees to 0.625 degrees. So previously what happened was the model used this kind of polar grid. So if you try to figure out where the pole is, it's somewhere inside of this extremely dense region of grid points. And that becomes an issue when you try to resolve structure and try to resolve propagation of the thermosphere and phenomena. And so that starts to limit what you can do, and it starts to limit the computation. It requires extensive computational power in order to resolve. And so to get around that, we don't need this high of a resolution in the polar region. And so what we did was we applied what's called a ring average filter. So this is what happens. We applied a secondary grid on top of that, which is a coarser grid that is an average of these points coming in, and then we solve on this grid as opposed to solving on this incredibly dense grid. So by doing it that way, we're able to increase the resolution everywhere and able to resolve better structures at the mid to lower latitude. So this would be the highest, the pole would be the highest latitude. So for example, these are two figures from TGCM. So you have the low resolution 1.9, TGCM version 1.9, low resolution version. And you can see there's these artifacts because we try to figure out a way to propagate structures across this incredibly fine number of points here. And so we've applied averaging techniques and other different things, and you kind of get these artifacts. With this new technique that we have, this ring average filter technique, we're able to increase the resolution and able to better propagate all these structures across the pole and better resolve the pole. And so this is a big improvement to what TGCM is capable of doing. So the next model is the Rice convection model. This was developed at Rice University. It's a model of the ring current and the inner magnetosphere. So you get this giant torus around the Earth. However, it's a 2D version. So instead of a torus, now you imagine kind of this disk going around the Earth, and that's the Rice convection model, which is it's a pretty good assumption for the most part. The ring current itself is formed due to charged ions and electrons drifting in different directions. So due to gradient B drift, your ions will drift in one direction, your electrons drift in the other direction. Since your ions are drifting in a different direction from electrons, separation of the two generates a current between them, and that gives you the ring current. And so depending on how much the number of ions and number of electrons you have in the ring current, that also determines the size and energy of the ring current. All right, so the next part is the remix, which is the re-envisioned magnetosphere ionosphere coupler. So similar to RCM, it's just a 2D shell that represents the ionosphere. So you pick a height of about 100 kilometers, you make a 2D shell around the Earth, and then you say that's the entire ionosphere. It's not this complex 3D structure, it's just this simple 2D shell. In which all currents in the magnetosphere will close. So all currents will enter the ionosphere on the shell, close across the shell, and then exit. It's the inner boundary of the magnetosphere, so we don't want to make it too complex, and then that makes it very difficult to solve. We just simply solve the Poisson's equations on a 2D shell. That's very simple. It takes no computational power to do. You give it a set of field line currents going in, you give it some sort of conductance pattern that's generated either by the ionosphere thermosphere model or some sort of empirical specification. And then it solves Poisson's equation and it gives you an electrostatic potential coming out. The electrostatic potential is usually converted into an electric field and then you apply the electric field onto the inner boundary of the magnetosphere. This electric field then starts moving a lot of the plasma that's in the magnetosphere, and then especially with frozen in flux, a lot of as your plasma on the inner boundary is moving, that moves the plasma within the magnetosphere in general. And then as a coupler, it does other things as well. It converts all of your MHD parameters. MHD stands for magnetohydrodynamics. It converts your MHD parameters into precipitation. It can do calculations for Poynting flux. It does some fancy things, such as trace your field line, trace your magnetic field line, so you know where you're connected to the solar wind and where it's closed. It does a lot of fancy things. So Remix it's kind of this simple model that does a lot of things. All right, so now we go to the magnetosphere part. Gomera. So Gomera is the new magnetosphere model. The other models are just advancements on older models, like the Rice convection model has been around for years, decades, maybe millennia, I don't know. And then the TGCM has also been around for about a millennia or so. Gomera is the grid agnostic MHD for extended research applications. The paper that describes Gomera's numerics was recently published in 2019. So it's a pretty new model. It's designed to solve MHD equations for a variety of problems. We've had people apply it to Jupiter, Ganymede, Venus, all sorts of different planets, maybe exoplanets. So it's pretty versatile. It solves the MHD equations on this kind of egg-shaped grid, which puts it's egg-shaped because you have in regions in which you're not in the equatorial plane, or you're not near Earth. So if you're near Earth, you care a lot about the structure near Earth. You care a lot about the structure in the equatorial plane because that's where your current sheet, plasma sheet, and a lot of interesting things exist, in addition to where your ring current exists. Once you're off the equatorial plane and you're a little bit off, a little bit higher or lower off the grid, you don't really care as much. And so the nice thing about the egg-shaped grid here is that you increase the size of your grid cells here in regions that you don't care about. But you also decrease the size of your grid cells in regions that you do care about. So this is the very nice advantage. It also saves you a lot in computation power. So if you took the smallest cell that we have and then tried to apply it everywhere, that's incredibly expensive. So this is the latest and greatest magnetosphere model. It's designed to run on the next generation of supercomputers, exascale supercomputers. I don't think any exist at the moment, but this is designed for the next generation. So for comparison, the older generation of coupled magnetosphere model, it takes about 9 hours of real time to simulate 1 hour of simulation time. And we call this quadres. So that's about half the resolution of things I'll be showing in this talk. Gomera completes quadres at 2 times faster than real time. So that's a huge improvement. This is 9 times slower than real time. Gomera completes at 2 times faster than real time. So it's, astronomically big improvement. All right. So that's the individual models. Let's discuss numerical resolving power. I was saying a lot about the different grids, but grid isn't the only thing that matters. You have your numerical scheme. So it's not about the size of your grid, it's how you use it. Efficiently using your grid requires good resolving power, which is a function of both grid size and numerical order of your reconstruction scheme. And transport advection scheme. So a high order numerical scheme does not require as fine of a grid to simulate. So if you have a coarser grid, you can get away with, or if you have a high order numerical scheme, you can get away with a coarser grid. If you have a low order numerical scheme, you'll need a much finer grid, but there should be some advantage to using one or the other. So I'll discuss a little bit about that. So the order of your reconstruction scheme and advection scheme. So if you're given the same grid, so the same number of points, higher order maintains the shape and transport better. So this left plot here is your initial condition. So given this kind of coin-shaped thing, if you propagate this forward in time using a second order solver, you get something that looks kind of smeared out and spread out because you're unable to maintain the shape and you're unable to maintain the full shape as it's as it's being moved that well. However, in the 7th order, you do a pretty good job. So if you took the slice, so this dashed line that you see here, and you just took that slice, and then you put that as a line plot, and then you did a comparison to see what, how much information is lost. You can see here that the blue line here is your initial conditions. This is very nice square well. Your second order reconstruction scheme gives you kind of this shape. It's smeared out a lot, especially kind of in the middle here, this region here, where you get some sort of smearing from both edges, and you're no longer at a density of 1 here. You're a bit elevated. If you use a 7th order reconstruction scheme for the same number of points, you do a much better job, significantly better. All right, so let's take a look at that as it moves forward in time. So here's your second order scheme on the left. So if you start at the beginning, you can see that the very beginning is the same shape. You have your second order on the left, 7th order on the right. If we move that forward in time, you can see that very quickly this starts to be diffused, and as it moves, you can see that it starts to kind of diffuse around the edges and gets a lot smeared out, but you maintain the shape much better with the 7th order here. So this is with the same grid, but as I mentioned earlier, you can increase the size of your grid in the second order in order to kind of help resolve your structure. You can just get a smaller grid because it's cheaper to resolve. All right, so let's do that. So how much do you need to increase your grid by in order to maintain the same structure? So with the second order grid here on the left, you need 1024 by 1024 in order to create this, in order to have this shape. For the 7th order, you're still only using 128 by 128. So you're almost a factor, an order of magnitude greater per dimension in order to resolve the same structure. So similarly, if you look at the density in the bottom here, you can see that the blue dashes here are all the second order. So you can see there's a ton of blue dashes in order to maintain the structure. And then, however, the 7th order, you can see there's large spacing in between your circles here, but you're able to resolve the same structure with much less grid points. So this is in 2D. In the magnetosphere and in geospace, a lot of things are in 3D. So in the magnetosphere, where it's 3D, you need an order of magnitude in every dimension, which gives you, 10 to the 3 times worse. All right, so resolving power is a function of both grid size and your order. So your L1 error here, so the L1 error is the difference between your target value, so the value that you expect it to be, and then the estimate based on what you're propagating. You can solve that using this equation here. So you have your target value, and then here's your estimate. You subtract that, and then you add that all up, and then that's your L1 error. So your L1 error is here on the left for a contrived case. The purple dashed line, you can ignore the purple dashed line. Take a quick look at the yellow line here. So the yellow line is the 7th order solver. The blue line is the second order solver. And then this is slope of a -2. So you can see that both of them quickly n is the number of grid points. So as you increase the number of grid points, you can see that quickly both the 7th order and the second order reaches about the same slope. However, in order to resolve the same structure, in order to reduce your error so that you can resolve and maintain the same structure as it propagates in time, it's about a magnitude of it's about an order of magnitude difference between the two solvers. And so that means that you can't just simply increase your grid size forever. You quickly run into a limit. The other thing is that when you increase your grid size, you greatly increase your computation power, your computation cost. And so it becomes extremely limiting when you try to increase the resolution. All right, so when you combine everything together, we end up with the highest resolving geospace coupled model. So Gomera uses the 7th order solver that you just saw, and it uses a very very dense grid because it does fancy things with the grid. And then because it's using a high order solver, we can continue to increase the resolution without as much of an adverse effect as you would with the lower order solver. All right, so to reiterate, Gomera's octres remix is about a ½ degree, TiGCM is 0.625 degrees, and then RCM is about a ¼ degree for latitude and 1 degree for longitude. Quad resolution, which I'll mention once more later, quad resolution is 2 times coarser than Gomera in every dimension. So in X, Y, and Z, you have a larger grid. All right. you do a lot of coding, you put everything together, and you get nice movies like this. So what you see here is you have the magnetosphere. This is the BZ component, the Z component of the magnetic field minus the dipole. So it's just the deviation from dipole. You have your pressure on the right, it's a log pressure, and then you have your remix solutions here. So the top panel is the northern hemisphere remix, the bottom one is the southern hemisphere remix, and then you have your RCM grid in the bottom left, and this is showing the pressure inside of RCM. So when you do a lot of things, you do a lot of coding, you put everything together, couple them all together, you get some nice movies and a nice simulation like this. So this is just a simulation of some random event, just to kind of showcase what's happening. So you can see with the high dense grid, we get a lot of features. You can see a lot of activity. We're able to maintain and propagate a lot of these bursts that are coming in, all of these flows coming in. And then as far as the remix grid, you can see there's a lot of structure, maybe too much structure. And that comes with that's one of the downside of increasing your grid, is that occasionally you start getting into unphysical regime. All right. All right, so now let's make use of that. And then I'll discuss neutral density and why neutral density is important. I haven't touched neutral density at all. I've just been discussing the different models, numerical resolving power, the geospace. Let's talk about the neutral density. All right, so quick jump is CHAMP and GRACE are two satellites. CHAMP is the Challenging Mini Satellite Payload, or also known as CHAMP. It's a bit of a stretch. CHAMP gives you CHAMP. Satellite launched in the 2000. It went down in 2010. Sits at about 416 to 476 kilometers or so. GRACE, it was a joint mission between NASA and Germans again, and that stands for the Gravity Recovery and Climate Experiment, GRACE. I think this is a little bit better than CHAMP. This was launched in 2002, and the mission ended in 2017. So it had a much better run than CHAMP, and it sits at an altitude of about 483 kilometers to 508 kilometers. All right, so why is this important? Well, you have to figure out how well your model is doing, and the way to do that is you compare observations from satellites to the results from your model. So that's one way to figure out how well your model behaves. The difficulty is that satellites is just a single point in space that moves, while your model is three-dimensional in space and evolves in time. So you have to figure out, trying to get them to match is very difficult, because if you have a structure that propagates and then misses, it's generated faster than reality, it's already propagated and gone before your satellite flies through it, that becomes an issue because you're not going to see it in your virtual satellite or in the model. So in order to match the data, you have to do a lot of things right in order to get single point measurements correct. All right, so why is the neutral density important? So I was just talking about these satellites. So these satellites sit at about 500 kilometers. That's within the TIDE GCM regime, which is well below the magnetosphere. So the magnetosphere starts, especially Gomera, starts usually at around 2 RE, or 2 Earth radii. That's at about an altitude of about 6,400 kilometers. That's pretty high up compared to 500 kilometers or even 400 kilometers. So these satellites are flying through the thermosphere as opposed to flying through the magnetosphere. But the input from the magnetosphere enters the thermosphere at the high latitude. So everything was coupled together. So changes in the magnetosphere will be seen in the neutral density. But then why am I looking at the neutral density? The neutral density is the last thing in a long line of, in a long causal chain. You have heat from solar radiation on the day side. You have Joule heating in the high latitude from the magnetosphere. You have particle precipitation that can ionize and heat up the thermosphere from the magnetosphere. You have pressure gradients within the thermosphere that can cause neutrals to be transported and move away and into regions. So there's a lot of transport that happens. You have chemistry that occurs. So you have, CO2, O2, things happen. You get ozone out of it. You can get O+ out of it. There's a lot of chemistry that happens. I don't know the details of all the chemistry. There's just a lot. And so all of this happens within the thermosphere, and then at the very end of it, whatever neutral, the number of neutrals left is your neutral density. And so neutral density is the very last thing within all of this causal chain. For satellites, especially Champ and Grace, they don't exactly measure the neutral density. What happens is they feel a drag force as they're flying, and then the drag force that they feel knowing the drag force on the satellites, you can estimate what the neutral density is from that. So this is just a quick diagram of what goes into and out of and what can happen to the ionosphere and thermosphere. So there's a lot of things occurring. It's just another version of the earlier NASA diagram. All right. So another movie. That's the nice thing about models. You get very nice movies. All right. So this is the northern hemisphere in the top left, southern hemisphere in the top right. The pole, the geographic pole, is located in the center. The sun is at the top, and then you have midnight and the night side on the bottom. And then this is a figure, this is the neutral density. One thing to note is that the color bar will change in time. You can see Grace flying through, you can see Champ flying through. They're single point measurements flying through this very complex three-dimensional space. And then in order to simulate and match what they're doing, you have to get a lot of things right. It's the very end of the causal chain again. And so you can see that as things start to happen in the polar region here, you see these waves start to propagate out. And you can see that every time Champ and Grace starts flying across these waves, right? You can see these crests and these waves, it's a spike. So the measurement is down here. Champ is at the top, Grace is on the bottom. And this is what Champ and Grace measures as far as neutral density. The colored lines is the result from MAGE, it's from the model. So you can see that every time Champ and Grace are flying across these waves, it generates a spike. But it seems that we're getting these spikes at the same time that Champ and Grace are seeing them. But the interesting thing here is that Champ and Grace aren't seeing these spikes at the location they're generated. These waves are generated at the high latitude, they've propagated away, and then Champ and Grace are flying through them. And then so we're able to propagate them at the correct speed with the correct amplitude. And that's what Champ and Grace are flying through. So like this peak here where my mouse is, this peak here was pretty far away from the pole, and then Champ and Grace fly straight through that, and then they're able to get a really good, as far as Champ here, Champ gets a really good match with the data here. We get the amplitude correct. Grace, we get close. It's not too far away. So that's the very nice thing about what we have here, and that's the nice thing about what MAGE can do, is we're showing that we're able to propagate, we're able to generate and propagate these waves with the correct amplitude, the correct speed. They propagate away at the correct speed, and then Champ and Grace flies over them, and we're able to match the data. Okay, enough about that. I've been saying that we match data. So how do we know that we match data? That's always a problem, right? You have a single point measurement flying through, and then I'm showing you these line plots. We've missed a lot of these, we've missed some of these peaks. We've missed some of these variability. It's hard to tell exactly how these match. All right. So before I talk about that, just a quick review of what the waves in the upper atmosphere are. So in terms of terminology, traveling atmospheric disturbance, atmosphere is the neutrals again. And so that's what you were seeing is traveling atmospheric disturbances, or TADs. And they're just disturbances, often waves in the neutral atmosphere. Traveling ionospheric disturbances are disturbances in the ionosphere. So the large scale ones that we were seeing, they will typically start at the pole and then travel to the equator and beyond, occasionally to the other pole as well. So these are large scale TAD and TIDs. They're often launched with the same mechanism. And so because both TADs and TIDs are generated and launched with the same mechanism, they'll have very similar properties as they propagate out. The medium scale ones for TADs and TIDs, they usually reach the mid latitudes. So instead of going from pole to pole or pole to equator, they'll go from like pole from 90 degrees to 45 degrees or less, 90 degrees to 60 degrees. It doesn't travel very far, and those are the medium scale ones. Some of these are generated in the model. We're still missing a lot of physics within the model, and including some of the physics and heating mechanisms would help us generate these medium scales. And so we do get a good number of these medium scales correct, which are some of these smaller variability spikes, some of these smaller amplitude spikes, and then the the very rapid spikes. A lot of these are from the MS-TIDs, medium scale TIDs and TIDs. So in terms of observations, the TIDs are slightly easier to observe because the ionosphere is filled with ions, and so ground radars can probe it. So this is a nice illustration of what a wave in the atmosphere would look like. It's kind of like a tsunami, except now you think of an entire pressure level, and then the whole thing, or pressure level, but you can imagine the entire atmosphere just rising up and then dropping back down. You don't really modify or change the local property. You just raise everything up and then everything goes back down. So you see these waves that are traveling through, and some of these can be very large scale and very large amplitude. So this is just to illustrate what a wave in the atmosphere would look like. All right, so in standalone TIGCM, the high latitude, so I've been showing the coupled model. That couples everything together, but each of these models can be ran separately and independently. So TIGCM by itself can be driven in the high latitude by either the Helix empirical model, which changes base every 3 hours, or the Weimar empirical model, which changes every minute. This changes based on the solar wind condition. Helix is based on some index called KP, and that changes every 3 hours. So the Helix is at the top here. You can see it does a terrible job. You can see it's very smooth and it misses everything. Grace at the top, Champ on the bottom. You can see that it just completely misses everything at Grace, and then it kind of does some of the lower end, the lower values of Grace okay, but overall it's not a very good model. Weimar, on the other hand, you can see, look at Weimar. You can see all these variability in Weimar. That's because it's varying on a 1 minute time scale. And you can see that it's able to match some of these peaks. Like it does a good job on this peak, does a good job on this peak, right? So you have, it does not too bad. All right, well, if it does not too bad, then how does it compare with our MAGE model? So the MAGE model is on the bottom here. Weimar's on top again, or not again, but Weimar's moved to top, and then MAGE is on the bottom. Looking at these, so you have Grace, Champ, Grace, Champ. How do you tell that we're doing better? If you look at Weimar, Weimar's getting some of the variability. We're getting some of the variability. We're missing a lot of these peaks. Weimar misses a lot of these peaks. How do we know we do better? Weimar overestimates some, we underestimate some. And so how do it's really a problem to figure out how do we definitively say we do better? All right. A quick comparison between what MAGE can do and what Weimar can do. MAGE has a very dynamic magnetosphere. Even though it's coupled to TIGCM, it updates TIGCM every 5 seconds. That doesn't really matter as much. It's more the distribution, because we have a full magnetosphere and inner magnetosphere coupled model. We're able to get a lot of the small scale structures and features of our distribution. So this is Joule heating here. This is the heating that's going into the ionosphere. And you can see that we have a lot of structure here. Weimar is an empirical model, so everything is smooth and averaged and kind of diffused out. So you can see it's a very large scale structure. It's very diffused, and it's quite different from what MAGE produces. So that's the main difference between these two models. All right. So now that you know the difference between the two models and how they measure, we have the analysis metrics. This tells you how well we do, and do we do better than Weimar? That's a good question. Weimar seemed to do a pretty good job. So the first thing is the mean square error. So the mean square error is the sum of the squares of the difference of the observation and model. Let's just ignore that. All right, the root of the mean square error is the square root of the RMSE, the square root of the mean square error, and that's calculated this way. So you just remove the square root here, and you can calculate the mean square error. So you take the difference between your observation and the model, you square that, and then you sum everything together. So the lower the number, the better, because the lower your error, the better you do. R square is the coefficient of determination. It's a fraction of the total sum squares, and explained by regression. Or you can take the correlation coefficient and then square it. If you're interested, you can just do a quick Wikipedia search for what is the coefficient of determination, and you get how to find it. All right. So what do they mean? RMSE is scale variant. What that means is that it tells you how close your point-to-point comparison is. It's an all-encompassing number. It's just a single number that tells you how well you do. It compares point to point, and it cares a lot about how close your values are. So the smaller your values are, the better you do. Or the smaller the difference between your observation and model, the better you do. R squared is scale invariant. That's also why it's called the coefficient of determination. What it means is it tells you how well the two correlate. So it doesn't matter how far away you are. If the morphology of one can explain the morphology of the other, then you get a better R squared. So the closer R squared is to 1, the better you are. So if you're exactly 1, then that means that the two models evolve exactly the same way, even if your RMSE is different. So you can have your RMSE different, and as long as they're evolving the same way, then you get a good R squared. So these two are very important parameters. RMSE tells you how close you are. R squared tells you how well you reproduce a lot of the features. And for comparison, this is the image model for the bottom. All right, so let's put that all. Here's a whole bunch of numbers. All right, so I split the whole thing into quiet period, which is this early period here. Then you have your main phase, active period, and then you have like a recovery period in the very end. And so, whoa, why did it jump so far? So in terms of RMSE, the smaller the better. Weimar gets 0.3. Mage gets 0.3. So you have quad res and octres. So changing the resolution doesn't seem to really change a whole lot as far as RMSE in the quiet period. We actually have a larger error than we do in Weimar. In the main phase, we have 1.7 for Weimar. So Champ and Grace are in between these this pipe here. So you have Champ and Grace, and so you have 1.7, 1.78, and then we increase that, or we decrease that. We get a much better agreement with the Mage model. So you can see that we do a lot better in the main phase. And if you look at the recovery phase, 2.3, 2.1, we do a pretty good job with quad, but then when you go to oct, you can see there's a significant improvement. And then all is just the whole run. The interesting thing here is if you take a look at Weimar versus Helix, in terms of the quiet, we can ignore that. If you look at the main phase, you can look, oh, Helix does a pretty good job. Look at the recovery. Helix does an even better job. Helix apparently does a really good job compared to Weimar, and it does a much better job compared to our quad res here. And if you look at the all result, which is the entire run, you can see that Helix does a really good job. All right, let's take a look at R squared. So closer to 1 is better. And if you take a look at the quiet period, you can see Weimar and Helix, with Helix doing slightly better than Weimar. And then that does a little bit better than the Mage. However, all the numbers are above 0.8. So all that means that all the models are doing a pretty good job. In terms of the main phase, we got 0.3 for Weimar, which is pretty bad. And then Helix gets 0.5. Helix is doing a pretty good job. I mean, it's doing a really good job. That's really close to what the Mage model is doing. So you have Mage quad here at 0.5 and 0.6 for Champ and Grace. And then you have Octres, it's about the same, maybe a little bit worse for the main phase. And then recovery phase is still about the same. So one thing you can draw as far as conclusion of this is that going from quad res to octres, increasing the resolution here, you don't change the morphology too much because the physics hasn't really changed. However, you greatly improve how well you do in terms of matching the amplitude and propagating, not propagating, but matching the amplitude, and how well you heat individual regions, and how well you create your structures. So you create them better with better structures, but you create them at about the same time. That's why you get a good R squared, right? All right, so going back to Helix. So, as I mentioned, Helix seems to be doing a really good job here. So my only conclusion for this is that Helix is the best magnetosphere specification ever. I mean, look at this thing. It matches everything, right? That's what the numbers say. But if you make a plot of the actual comparison between Helix and Champ and Grace, it is by far the worst, by far. So in conclusion, you need to do a comprehensive analysis. You can't just look at the numbers. You can't just look at the plot. You have to use both to figure out how well you do. Some of the spikes seen by Champ and Grace are actually waves that are propagating. And then in order to get the waves and match what Champ and Grace get, you have to do a lot of things right. So Mage captures them reasonably well. And this represents a significant improvement compared to the standalone TGCM. You saw in terms of the distribution, in terms of the line plots, they kind of look the same, but when you look at the numbers, you can clearly see that Mage model is a significant improvement over the standalone TGCM. And then increasing the model resolution seems to improve how well we match the observed value. It doesn't necessarily change the morphology of the system so much. All right, and that's the end of my talk. Thank you.
Awesome. Well, really nice talk, Kevin. Thanks for sharing with us. So I hope you can see here. There's some applause, some silent applause popping off in emojis in the participants list. So so thanks again, and yeah, so we'll open it up for Q&A here. Anyone, feel free to jump in. Give people a minute to come off mute. Well, while people are coming off mute here, I'll ask one question. So now that you've gotten us all excited about the MAGE model, proved that it's really promising. I'm wondering at what point will the rest of us online get a chance to start making runs?
Oh, that's a good question. It depends on whether you want to learn the entire, how to compile and install and run it yourself, or get access to your own supercomputer and do all of that, or you can contact CCMC and then get them to do that for you. So we've been collaborating with CCMC to get them up to speed with running this model, and then eventually, probably a year or two, I think Slava can probably mention better in terms of timeline, CCMC will have this up and running and available, and then so everybody else within the community can get the runs themselves.
Definitely earlier than a year or two. I mean, they're onboarding right now. It's going to take them some time to kind of set things up, but it's probably months.
So within months, you'll be able to do this.
Excellent. Well, thank you. Harlan, you want to jump in here with your question?
Yeah, thanks, Kevin. So Kevin, I have a question about the future, and it's really kind of getting an inside look from your perspective of what's needed for the next major sort of step forward, or not really step forward. What I'm really looking for is leap forward. So there are probably a lot of things that you can do with the current architecture and so forth to make great progress, but it may be more stepwise. So to make the next big leap forward, is it going to be software? Is it going to be computational? Is it the hardware? Could you speak a little bit about what you think it will take to make that next big leap forward in numerical model?
That's a really good question. So the next big leap forward has to do with all of the above to what you mentioned. So you have both software side, improvements in physics, as well as in terms of hardware. So the big leap forward is, one, we need to figure out what physics we're missing, and then we need to include those physics, either by including them directly into existing models, creating new models, or tacking on additional models. So the biggest leap forward that right now would probably be, there's a lot of models that currently aren't included. So for example, everything I'm showing is using a single fluid H plus assumption. So everything is just hydrogen ions, such as protons or electrons, and that's pretty much it. So we don't have O plus, we don't have a lot of the heavier ions in the model right now. So a big leap forward would be moving towards that direction, including additional fluids into the magnetohydrodynamic solution, and then solving that way. So in order to do that, we would need an entire ionosphere model that can handle all of that and provide the O plus from the ionosphere into the magnetosphere, as well as, it would be entirely coupled in. So just including more models is one way to be a leap forward. This current model is already a big improvement to existing models. And so including more models is really an easy way to go.
Thanks.
Any other questions? All right, well, I'm not hearing any more, and I'm not seeing any more hands raised. So thank you again, Kevin. I really appreciate it. That was a really nice talk, very accessible to non-modeling experts like me. So I really appreciate that. And yeah, thanks again for coming by and sharing your research.
Yeah, thank you for having me. I guess one takeaway is that we do need a lot more observations as well. I mean, for example, I only have 2 points for this.
Hey, that's something we can all agree on. Excellent. You know, and I should point out too here, the danger of coming by here and doing a good job is we will invite you back in the future. So so you can expect to hear from us again in a future semester. And
yeah, I would be glad to come back.
Excellent.
Maybe in person next time.
Yeah, hopefully. Yeah, not too much longer. Awesome. Well, well, thanks, and have a good one. I'm going to stop the recording here.